Chapter 3.5, Implicit Differentiation. Now, what is implicit differentiation? It is a brand new method of finding the slope of a curve, or the derivative, when that curve is no longer a function. Okay? So, for example, classic example is a circle. A circle is not a function, definitely has these slopes, but it is not a function where I can solve for y. Because, for example, I'll have this curve, which is x squared plus y squared, is equal to, if the radius is 5, 25. Right? Now, can I solve for y? We can try. Y squared is equal to 25 minus x squared. Y is equal to plus or minus the square root of 25 minus x squared. Now this is not really a function. If I wanted to write it as a function, I'd have to split it up into two different functions. First being the positive square root of 25 minus x squared. The second being the negative square root of 25 minus x squared. And you can go about it exactly the same way. If you're given a point on the positive side here, you can use the top equation to find the slope. Or if you're given a point on this bottom end of the circle here, you can use the negative function. But cases are not always like that. So for example, if you had a case that looks something like this. X cubed plus y cubed equals to 6xy. This is not a function because it fails that vertical line test right here. And you can't really solve for that y. You can't get that y by itself. So that's why we're going to need a new method of differentiation called implicit differentiation. Now, implicit differentiation is basically coming from the chain rule. The chain rule states that if I want to find the derivative of this this y with respect to x, I take the derivative of the outside function, so cosine, keep everything on the inside the same, and then multiply it by the derivative of this inside function, which is 2x plus 2, right? What implicit differentiation does, it's exactly the same thing, except it's kind of like it's using a u substitution. So it's saying that u here is equal to x squared plus 2x, right? And then the derivative of that inside u with respect to x is going to be 2x plus 2. Now what does that look like? Well, I'm taking that dy dx, taking the derivative of y with respect to x, and it's going to equal to the derivative of cosine of u, right, because this was just u, and everything on the inside stayed the same, times du dx, the derivative of that inside. Now this is kind of the form that we are going to stop at in terms of implicit differentiation. We're saying that we cannot find the derivative of u because it is not with respect to x. So we can find the derivative of that shell on the outside, find the derivative of sine x to be cosine x. We keep the u inside, keep the inside the same, and then we take the derivative of that inside of u. And then in this case, we can always substitute the u back, and it is in terms of x, so we can find the derivative of that. Now, it is based upon the chain rule, but here is what it actually looks like in reality. So we're going to go back and take the derivative of this x squared plus y squared equals 25, this circle. Okay, we're going to find the derivative function here. Well, not function, derivative equation, I should say. What this basically does is this derivative, we want to find the derivative of y with respect to x. Now that is very important. This x, I learned calculus at the same time that I learned biology when we were learning about DNA translation. So it's kind of like I'm translating this sentence using my little math ribosome here, my derivative ribosome. I don't know if you guys took biology yet. But it's basically, I'm taking the derivative with respect to x, and that is the most important part. Now, if I place this right there, the derivative of x squared with respect to x is easy. It's just 2x, right? If I move it over to here now, derivative of y squared with respect to x, I cannot recognize that y. But I can use the chain rule to say, well, I do know that the outside function is a square function. So I can find the derivative of the outside function, which is 2y, And this y I cannot recognize because I am translating with respect to x. So I still have to take the derivative of whatever that y is with respect to x. Okay, so it's the outside 2y times the inside, which I cannot find the derivative of, so I'm going to keep it as dy dx. Is equal to, and then I'm going to take the derivative of a constant with respect to x. For a constant, it will always be 0. And now what I can do is I can solve for dy dx. I'm going to minus 2x to both sides, and then divide both sides by the 2y. And I'm going to get it equal to negative x over y. Right? So now this function right here is going to represent if I'm given some sort of a point on the curve. Let's say 5, 0. Right? What is the slope at 5? 5, 0 is going to be undefined. Slope at 0, 5 is going to be 0, because 0, 5, right? If I'm given some sort of a point on the curve elsewhere, I can actually find the slope of that line no matter where it is. But I have to be given both points, x and y, both coordinates, x and y. Now let's take a look at another one. This one right here, the same one that we looked at before, where the graph looked like this, right? We want to find the tangent line, and here I am given a point 3, 3. 3, 3 looks like it's somewhere around here maybe, yeah? We want to find the slope of that line if we're looking for the tangent line. Now in this case, again, I cannot isolate that y, so I must use my little implicit differentiation. So I'm going to translate this sentence. I'm going to send this little ribosome through. So in this case, the derivative of x cubed with respect to x is easy, 3x squared. If I send this over this way, the derivative of y cubed with respect to x, I don't know how to find the derivative of y with respect to x, but I do know how to find the derivative of this outside cube function. So I'm going to take 3y squared, just like the chain rule, times the derivative of the inside, y, which I can't actually find, so I'm just going to leave it dy dx, is equal to, and now I am going to have to use the product rule here. So let's try it. It's the first term. I'm going to chunk these two together as the first term, 6x, times the derivative of the second term. Now this derivative of the second term, again, I cannot recognize, plus the derivative of the first term times the derivative of the second, plus the second term times the derivative of the first. Derivative of the first term is easy because it's with respect to x. It's just 6. I'm solving for dy dx, so I'm going to get all of dy dx onto one side. That means I had the 3y squared minus 6x on this side. So I move this term over that way and factor it out. I'm going to move minus the 3x squared. Actually, I'm going to say the 6y here, minus the 3x squared here. You can pause it if you need to figure out which steps I skipped. I did skip a load. 3y squared minus 6x. I am going to factor out all of those 3's, 2y minus x squared over y squared minus 2x. Is that a 2? 2? Equals dy dx. Now the question was asking for me to find the tangent line at 3, 3. Now again, 3, 3 can be anywhere over here, so the slope at 3, 3, dy dx at the point 3, 3 is how you write it, is equal to 2 times 3 minus 3 squared all over 3 squared minus 2 times 3. Right, so I get 6 minus 9, I get 9 minus 6, I get negative 1. Assuming it's somewhere here, I get a slope of a perfect negative 1. That is my slope of the tangent line. Of course, I'm going to use my point. So y minus y1 is equal to the slope x minus x1. And this would become the final tangent line of this curve at the point 3, 3. Now next, let's try that again. So we're taking that same implicit differentiation and we're going to practice it with sines and cosines now. So we're finding the first derivative of y, dy dx basically. So I'm going to take that and I'm going to find the derivative of the first. with respect to x. So it's the outside shell. This is now definitely the chain rule. It's going to be the derivative of sine x, which is cosine x. Keep everything the same. Times the derivative of the inside. Now again, if I'm looking for the derivative of the inside, I have to send this through. Derivative of x with respect to x, and then derivative of y with respect to x. So that's going to give me 1 plus dy dx is equal to, I'm going to translate this, and this is going to actually be another product rule. So we'll have the first times the derivative of the second with respect to x, so that's good, plus the second times the derivative of the first, which is going to be 2y, and then again, I cannot recognize that y, times dy dx. It is like the chain rule. All right, so let's practice getting all of this dy dx out. It looks like, let's see, I'm going to move all my dy dx out. Let's distribute. So I'm going to get cosine of x plus y plus cosine of x plus y times dy dx is equal to negative y squared sine x plus 2y cosine x dy dx. I multiplied everything out. I have 4 terms. This term and this term both have the dy dx, so I'm going to bring all of that to one side, and I'm going to factor out the dy dx. I'm going to bring everything to the left, so this is going to stay positive, cosine of x plus y. This is going to be negative because I subtracted it to both sides, and I factored out the dy dx. In this case, I'm going to move everything over to the other side, so this term on the right stays negative. I'm going to minus the cosine of x plus y. Once you get that, you get dy dx is equal to negative y squared sine x minus cosine of x plus y all over cosine of x plus y minus 2y cosine of x. I would just do one more fix and just switch these. So that, let's see, yes, so y squared sine of x plus cosine of x plus y, just to clean it up a bit. And then on the bottom, I get 2y cosine of x minus cosine of x plus y. So this would be my y prime. Last example, second derivative. If I'm looking for the second derivative, what does that look like? Well, once again, let's start translating it. I get, again, 4x cubed, super easy. Moving it over, I cannot recognize this y, but I can use a chain rule. 4y cubed times the derivative of the inside is equal to, the derivative of a constant is just 0. I do have to, before I start taking the second derivative, it does make it easier to get that dy dx by itself. I get negative 4x cubed over 4y cubed, so I get negative x cubed over y cubed. Now what I'm doing is I want to find the derivative a second time. So I'm pulling this through here and here. I'm differentiating one more time. Now what does this look like? If I'm finding the second derivative, a derivative of a derivative, well, look at what doubles up, and that's almost exactly how you write it. It's d times d squared y, over dx squared. Okay, I guess it would be this in parentheses, but that's not how it's written. This represents the second derivative. And then when I bring the derivative translator over to the other side, I am taking the product rule here. So bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now let's try simplifying this a bit. So I get negative 3x squared y cubed. This looks like it becomes a positive x cubed. There's a 3y squared and a dy dx all over y to the 6th. Now this embedded inside my second derivative